Hi, everyone. Thank you for coming. I come from University of Southern California, Information Sciences Institute, and I'll be talking to you about a research system we've developed for distributed attack defense. This is joint work with Minlan Yu and Abdulla Alwabel from USC and Ying Zhang from HP Labs. My primary reason for being here, this is my first NANOG, is to get community feedback about this system, if it seems deployable. I don't know if there's I hear some echo. Am I too close, or is it fine? Okay, so we would like to know if the system seems deployable, if we've overlooked anything, if our assumptions are realistic, and if anyone is interested in pilot this, we will have a prototype soon, so we would like to talk to you. So I'll start with the motivation and insights we had. We looked at distributed attacks on the internet. I've worked myself in denial of service area for 15 years, and we just have ongoing trend of the attacks getting more frequent and stronger, and we have very few solutions for them. So this is the slide showing the trend in denial of service area. It's borrowed from the Arbor Network annual report for 2014, where 2/3 of the networks say they've been hit by a DDoS attack, and the volume of the attacks has skyrocketed. In the Prefix hijacking area, the Renesas Corporation publishes an annual report showing the frequency of the attacks, and in 2013, 1,500 prefixes have been hijacked in 150 cities. You can see that these are distributed all over the world, and the attacks have lasted sometimes for 60 days. So imagine losing your traffic for 60 days. The traffic for major companies and governments and ISPs has been affected by this. And so the attack variants that we wanted to focus on in our work are in DDoS field, direct floods, reflector attacks, and crossfire, and in BGP prefix hijacking, origin and closeness attacks with blackholing or interception. So I'll go quickly over these just as a refresher. The yellow dot is representing the victim, and the red dots are the attackers in these pictures. And during the direct floods, the attackers send high-volume traffic to the victim that overwhelms its network. In reflector attacks, the attackers spoof the victim's addresses in service requests, for example, DNS requests. They send them to public servers, usually open resolvers, and these servers reply. These are usually much larger replies than the requests were, and this traffic overwhelms the victim. The crossfire attack is something that has been proposed in the academic community. I don't think we've seen it in the wild. Some people tell me that this would not be really a problem in the operational world, but this is something that academics have been looked at. The crossfire attack has the attacker send traffic from many sources to many destinations, but the destinations are smartly selected so that the traffic converges on a single link in some given ISP. This happens to be the link that the legitimate traffic crosses from clients to the victim, and that's where the congestion occurs, that's where the traffic gets dropped. This is far from the victim. The victim does not see congestion. It just sees that it's losing traffic. The ISP sees congestion but cannot diagnose why it happens because there are many sources communicating to many destinations in the traffic. In BGP prefix hijacking, we look at origin and closeness attacks. In origin attacks, the attacker announces the prefix of the victim and thus attracts the traffic. In the closeness attacks, the attacker claims to be close to the victim, so he claims the short AS path, and that's how he attracts the victim's traffic. And once he attracts it, he can drop it. This is the blackholing attack, or he can modify it or sniff it and forward on to the victim. That's the interception attack. So looking at all these attacks, we ask, what is the thing they have in common? And the thing they have in common is that they are really hard to mitigate and diagnose from the victim's perspective, because the victim needs to observe traffic and routes in remote networks to diagnose the attack sometimes, and to mitigate it, it needs help of the remote networks for the mitigation. In DDoS case, to drop the traffic. In BGP prefix hijacking case, to fix the routes that have been polluted. Especially in the BGP prefix hijacking case, I'd like to point out that the routes that are polluted are usually polluted in the networks that are far from the victim. These are the networks that will adopt the attacker's route because it will be the shortest one. So our insight was that we need help of remote ISPs for attack diagnosis and mitigation. And we came up with the idea of SENSS. This is the framework, the system that would be deployed by ISPs that the victim could talk to on demand when it's under attack. And it would enable the victim to observe its own traffic. We define own traffic as traffic going to the victim's prefixes or carrying the source IP from the victim's prefixes. It could control its traffic. You can think of SENSS as enabling a distributed firewall where the victim can filter or allow traffic to its prefixes, but these rules are installed in remote networks. It could observe its own routes, so routes to its own prefixes from remote networks, and it could control these routes by demoting some routes that have the attacker segment or asking for the route to be corrected by replacing some segment of the AS path with a different segment. So now I'll tell you more details about how SENSS works. ISPs run SENSS servers, and victims talk to these servers when they are under the attack. They could discover the existence of these servers through some public directory, for example, through DNS. And when the victim is under attack, it would select which ISPs to talk to. It would send a query, either about traffic or about routes, receive responses, figure out where to act on the traffic to filter traffic or where to correct routes, and then send control messages that would then be implemented by ISPs. Of course, all this requires very well thought and foolproof security layer, because we don't want people affecting anybody's traffic or routes except their own. And we have mechanisms to ensure that, and every ISP, when they receive the request, would actually authenticate the request, verify the ownership of the prefix, and then act on that. We also envisioned that ISPs could charge for this service, so this could be an add-on service. They wouldn't just do it for free, although I guess we don't quite understand how the operational world looks like. Maybe people would do it for free. That's what I'd like feedback on too. So we made two key design decisions. First was that we wanted this to be implementable today in today's ISP infrastructure. So we have very simple actions in ISPs that can be done with today's infrastructure, and all intelligence resides at the victim. So the victim collects this information, decides what to do, and then asks for control actions of the ISPs. This also has the benefit that the victim decides about its own traffic and routes, so it aligns the ownership of traffic and routes with the control over these. And this is good because there are many trade-offs in DDoS and prefix hijacking. It's usually not clear-cut what to drop. It's usually not clear-cut which routes to fix and how. And so the victim, the repercussions of having the bad decision means that some legitimate traffic might get dropped. Victim is the one that has enough insight to make these decisions. It understands the priorities of its operation. It can understand what the consequences would be if certain types of traffic get dropped. We also made the second design decision to support direct victim remote ISP communication, and what this enables us to do is in a very sparse deployment, if the SENSS is deployed in key points in the internet, then everyone can benefit whether they peer directly with the SENSS ISPs or not. So this is a quick comparison with the state of the art. I tried to focus only on the either solutions that are currently deployed in the operational world or those that could be easily deployed. There is much more related work that I'm not showing here, and I won't go in detail through this except to point out that our goal was to handle large variety of attacks, because attacks are relatively frequent in the internet, but they are rare for any given victim. So if the ISP is to market this service to its customers, it better be able to handle many different attacks so that the customers may use it relatively frequently. We handled all the attacks that I've listed on the motivation slides, so direct floods, reflector attacks, and crossfire, and then blackholing and interception, prefix hijacking with origin and closeness variants. The Other solutions in this space only handle a few of these attacks. And I would like to focus on two solutions that are relevant to us, the commercial DDoS defenses, such as Cloudflare and Prolexic, and secure BGP. So Cloudflare, Prolexic, and many similar DDoS defenses work by diverting the customer traffic through a CDN-like structure. They have wide presence on the internet, and then so that helps sustain the attack. And they also have proprietary algorithms and deep packet inspection. They try to scrub the traffic. They try to figure out what's the attack and remove it and let just the legitimate traffic through. In some cases, this solution will actually be more accurate than what SENSS can do, because SENSS works at the header level, not at the content level. And we made this decision on purpose because, as I said, we wanted it to be deployable in today's network infrastructure. However, the DDoS mitigation solutions that exist today concentrate traffic in this CDN-like structure, and this can lead to other problems where attackers can go after links that peer with the DDoS defense provider or go after the DDoS defense provider's infrastructure itself. That was the case during spam house attacks, where they couldn't bring spam house down because it was using Cloudflare, but they went after Cloudflare and they went after certain peering links that Cloudflare had. And for some limited amount of time, this created problems for bystanders, for traffic that was just traversing this infrastructure, going to other places. And so we believe that SENSS is a better solution because it could have wider reach. It does not divert traffic. It just works with the current routes that the traffic takes, and if there is an ISP deploying SENSS on this route, it can have a great benefit to the victim. In secure BGP direction, the secure BGP can mitigate all the prefix hijacking attacks by doing heavy crypto, it validates both the origin of the route and every hop in the AS path. However, to fully secure the path, you need full deployment from the source to the destination. That's hard to ensure in today's internet. Nothing will ever be fully deployed everywhere. We believe that we need something that works in sparse deployment and has actually good performance in sparse deployment so that people feel motivated to use it. And we believe that SENSS is this solution. It uses RPKI for origin authentication, but then the AS path is not authenticated. We just detect when there are attacks that misuse AS path, the closeness attacks, and then we can correct for those. So these are the SENSS APIs at ISPs. I won't go through each of them, except to point out that you can ask about your traffic or routes. If you ask about traffic, what you get back from the ISP is the distribution of traffic over the neighbors of that ISP. You can tell which neighbor sends which traffic, what volume of traffic to your prefixes using this ISP. So you can identify AS to AS links and the volume of traffic they carry to you. In the route query, you ask about the best route and you get the response. When controlling traffic, you can ask for traffic to be filtered or allowed. We originally proposed that you can also ask for bandwidth guarantees. Listening to the FCC talk, I learned that this is actually not in line with the net neutrality, so we'll be looking how to fix that, but this is just a small part of SENSS, and it's really not critical. We can actually drop that. And then in the route control, you can ask for routes to be demoted if they have a certain segment, or you can correct that segment. You can ask to be replaced for a different segment. We envisioned that SENSS would be deployed at ISPs as a web service, and we made this decision because there are a lot of functionalities that web service currently has that we can leverage. For robustness, we can leverage replication solutions to web services. For security, we can leverage HTTPS, and if ISPs were to charge for this, we can leverage e-commerce solutions so people can sign up on demand and start using SENSS. Now I'll talk about security. Security is very important. We don't want people controlling anybody's traffic or routes but their own. And so we propose use of RPKI to verify ownership. You can only, when you send requests for SENSS services, you attach the RPKR certificate, the ISPs validate it, and only if it's valid, they will take actions. So you can only affect traffic for your prefixes and routes for your prefixes. Also, to address attacks in the middle, we use TLS, that's a common for communication security. Further, victim might be so overwhelmed with the attack that it cannot communicate, not even with SENSS. Maybe its prefixes are hijacked, so it cannot receive replies from SENSS, and that's bad because victim needs to observe in order to learn what to do with the traffic and routes. Or it may be so overwhelmed with the DDoS attack that it cannot receive replies again from SENSS servers. What victim can do easily with SENSS is offload the victim functionality to, say, a cloud in a different network. If the victim prepared a proxy or several proxies in several different networks in advance and gave them the prefix ownership through route authorization, through RPKI, then these proxies can act on behalf of the victim when the victim is disabled. So I'll now briefly introduce how we could use SENSS to diagnose and mitigate attacks, and I'd like to point out that these are just examples. SENSS APIs are very simple, so you can combine them, the customer can combine them in any way they see fit. In case of direct floods, if there is a TCP/IP signature, the handling is simple. The victim would choose the ISPs to communicate with and just ask them to drop the traffic. This is similar to FlowSpec used today, except that it works with remote ISPs and it adds a layer of security that does not currently exist in FlowSpec. If there is no TCP/IP signature, traffic is coming from everywhere, and it's hard to separate legitimate from the attack. The victim can use SENSS to identify links between the neighbors of the SENSS deploying ISP and that ISP. So it identifies the AS to AS links that carried little traffic prior to the attack to the victim and now carry a lot. And these links are prime candidates for filtering because they are likely to carry most of the attack. I will illustrate this with an example. This is a simple example of a DDoS attack. Prior to the attack, the blue traffic flows to the victim. Imagine that only the gray nodes are the nodes deploying SENSS, so A, D, G, J, L. The victim periodically queries them about the volume of traffic they receive from their neighbors, and it learns that link AB carries most of the traffic to it during regular operation. When there is an attack, it queries again. It now learns that link LS2 carries a lot of traffic, whereas it did not do so before. Link JK carries a lot of traffic, whereas previously it carried just a little. And so these are the links that are prime candidates for filtering. The next step would be for the victim to ask for filters in L and potentially in J to filter the attack. We have a solution for reflector attacks that we believe would be able to surgically remove the attack traffic. Reflector attacks are mostly unhandled today. What we propose is that the victim could NAT all outgoing traffic to the service that is affected, that is misused in the attack. For example, if the attacker is making a lot of DNS requests, then port 53 requests would be, port 53 traffic would be netted at the victim, and the victim would choose a range of source ports that is secret, known only to the victim. This range is A to B. And then it would send 2 control messages to ISPs asking them to let only replies to the net IP and to range of ports A to B from the port 53 and drop all the other replies. And of course, if there are only 665,536 ports, so the attacker can probe and figure out which port range the victim is using and then focus its spoofing on that. But the victim can dynamically keep changing this range because SENSS is fully automated. In the interception attack, this is the attack where the victim's prefix is hijacked by the attacker. If the attacker announces the prefix, RPKI takes care of that, so we don't have to do anything special with SENSS. However, if the attacker announces short path to the prefix, this is the attack that is very hard to diagnose and to mitigate today. Using SENSS, the victim can ask the deploying ISPs for their control plane path, so it asks about routes, and it forms this control plane path set, CPPS. It also can ask about the data plane path, about where traffic is coming and going when it's going to the victim's prefixes, which neighbors of the ISP send and receive this traffic. And from that, it forms the data plane path. Now, looking at the intersection of these two, if there are segments of ASPath that are in the control plane but not in data plane, these are prime candidates for having been the fake segment, the fake parts of the segment of the route announcement that the attacker made, and these are the segments that can be corrected either by demoting this route or by correcting the segments. So I'll illustrate this quickly. In this picture, H is the attacker. It announces path HGV to the victim, so it's doing the closeness attack, and this attracts the traffic from the ASs that are close to H. Again, only gray ones are deploying SENSS. Victim can ask the SENSS deploying ISPs for their control path, and it learns from G and L that their control path is going through H and then G and to V. But then through asking about the data path, it learns that G receives traffic from H but sends it to F, and victim knows from its own observations that it receives traffic from E. So it assembles the data path that is different from the control path. Looking at these two, there is GV segment that appears in the data path, but not in the, sorry, in the control path, but not in data path. So the victim can ask for any route that has a GV segment to be demoted. I'll talk briefly about the evaluation. I was cautioned not to mention word simulation in this meeting, but unfortunately we are at the university and we have to work with simulations. However, we also wanted to answer the question how this would do in sparse deployment, because that's what we care about. If this doesn't do well with first few adopters, then no one will ever deploy this. So we constructed an AS-level topology from route views. We looked at several partial deployment scenarios. What if only a small ISPs deploy this? Or what if a mix of small ISPs and tier 2 and tier 1s deploy this? And in these mixes, 70% would be small ISPs, 25 to 30% tier 2s, and 5% tier 1. And we went up to 200 ASs, which is half of the percent of the current AS population, and it's 15 times smaller deployment than current deployment of RPKI. For some of these simulations, we needed to assume some things about attacker distribution and legitimate traffic distribution, and we used both realistic traces from Edgecast for legitimate traffic and from Bars Group at CMU and UCSD for attacks. And we also looked at just random choices of attackers and legitimate clients. And all these simulations had the similar conclusions. I'll just show you a few of those. In case of DDoS reflection and direct flood with signature, I'm showing you the benefits that under different deployments, the benefits that would be experienced by direct customers of the SENSS deploying ISP. These are the red and the yellow bars. The yellow bar is for multi-homed customers, and the red bar is for single-homed, and then the brown bar is for everyone else. So what if someone anywhere in the internet wants to use SENSS? And you can see that direct customers have huge benefits that's given because they work directly with their ISP, they know what to filter, and the ISP just filters it. However, when we have tier 2 deployment, or tier 1 deployment, the benefits become huge, not just for direct customers, but for everyone else, because there is high probability of attack traffic hitting one of the SENSS deploying ISPs, and again, because the signature is so specific, it can filter the attack. In case when there is DDoS flood without signature, this is the case when we have to identify these AS links that did not carry much traffic before, but now do and are likely carrying attack. In small ISP deployment, we don't have good performance, mostly because you really need wide performance to catch the attack. If the attack is not traversing your deployment point, you cannot do anything with it. However, when you do have deployment in Tier 2 and Tier 1 ISPs, and this is, again, very small deployment, it goes from 20 deployment points to 200, and only 25% of those are Tier 2 and 5% are Tier 1s. We have huge benefit for both direct customers. Again, direct customers have more benefit than remote ones, but everyone else experiences benefit. Similarly, for interception attacks, we need deployment in Tier 2s and Tier 1s to have benefit. When these deployment points correct their routes, then the corrected route propagates to their neighbors. Even if they are not deploying SENSS, it propagates just by using BGP. So I'll talk briefly about deployment considerations. The biggest feedback we've got from operational world is that there are concerns about privacy and policy that ISPs have, and we understand that this is a big change in the culture, opening your ISP for anyone to insert control and observation messages in it. We believe that the structure we've imposed on these APIs helps understand the risk, and we believe that the risk is very small to non-existent. So routing information is already public. Traffic information, there is sensitivity in ISPs about load balancing, and if asking about traffic would reveal load balancing decisions. However, the neighbor information and the volume in the replies, when you're asking about traffic and you're getting this reply that tells you about distribution of traffic over of the neighbors of the SENSS deploying ISP, this information can be anonymized or aggregated, and SENSS can still work well, but you're preserving the privacy. Finally, the ISP can always refuse to take any action that goes against its policy. So this is just a service that is offered. The customer asks for service. The ISP can refuse, for example, if the customer is asking too many questions or asking to demote routes that are especially desirable for the ISP and have been around for a while, the ISP can refuse. Talking about charging, we would really like your feedback. We envision that ISPs could charge fixed price or on demand, and we believe that on demand makes more sense because victims are infrequently affected by these attacks and disproportionately, and it would be nice for them to sign up when they are under attack, to sign up in an automated fashion, and to reap the benefits and pay only when they are using the service. We looked very closely into misbehaving ISPs and what would happen if someone is lying or someone is underperforming. And the good news is because of the SENSS design, where all intelligence resides at the victim, and victim is only asking about the particular ISP's view of the world, lying cannot really affect us. It only increases the cost of the victim because the victim pays for services that are not rendered, and it may delay the correct decision at the victim, but the victim will not make a wrong decision because of it, will not filter legitimate traffic or correct a route that does not need to be corrected. So to conclude, we believe that distributed attacks are not handled well today. The focus today is on sustaining the attacks, but the real fix is dropping attack traffic and fixing routes that have been hijacked. And so we believe that SENSS can help in this regard. It can help detect and mitigate distributed attacks. It has good performance in sparse deployment, and it's simple to deploy with current infrastructure. So we believe that these are good news, and we hope to motivate wide deployment. Ultimately, we view SENSS as a first step towards future infrastructure for ISP collaboration. With these simple APIs, we can handle not just current attacks, but future attacks, and we also believe that there are many cases that are not security related. For example, there are natural catastrophes that affect routing in some part of the internet, and SENSS could be used to detect that and to mitigate it. So thank you for coming. Please reach out to us if you're interested to learn more, or if you're interested to deploy this. We will have a prototype maybe by the end of the summer. These are our pictures and our names and our project webpage and my email address. And specifically, we would like feedback from both ISPs and customers. If we overlooked anything, again, we're coming from academic world, we're newbies to this, or if there are any other attacks that we should look at, how likely you would be to deploy this, how would you charge, anything that you can give me would be appreciated. Thank you.
Question.
Randy Bush, IJ and Dragon Labs. First of all, hot stuff. Thank you very much. One pedantic comment. RPKI is a database. It doesn't check anything or validate anything. You are specifically using RPKI-based origin validation.
Yes. Thank you, yes.
Okay, there is also, in prototype and test, RPKI-based path validation, which will help address future issues there. But I just wish everybody here would be careful with the term RPKI. It's just a PKI. It's how you choose to use it.
Right, thank you. Any other questions? Comments? Don't be shy.
One question. BCP38 and RTBH have been around a long time. And one of the things that can be said for them, and one of the reasons that they're widely utilized, is because they are standards-based. In any of your work, is there anything being done to incorporate this in the current standards, which these other principles or engineering tools that already exist are thus given the necessary respectability to enable widespread use?
You're referring to the ingress filtering, BCP38?
Yeah. Again, what you presented here is, seems like in some ways a follow-on and hopefully an improvement for certain, mitigation tools that are already used.
Right.
And the mitigation tools that are already used are standards-based. So my question is part of the process to propagate the use of SENSS is to make it in any way standards-based, or is that discussion not relevant to SENSS?
Frankly, we have not thought about this yet. It would be great direction to think about. Thanks. Okay, thank you.
Thank you, Jelena.